Hi friends, today we are going to see the second part of the experiment number 7, that is called PID control of mechanical system using suitable simulation software, and that simulation software is nothing but Simulink. In the last video we have seen the introduction of the PID control. We have seen the different terminologies in PID control. I will just have a look. We will have a look on that. This is the process variable, set point and all. Here we are using on-off control, but this is the graph of this sinusoidal graph is the graph of on-off control. And this, what are the limitations of the on-off control? The on-off control is suitable in the household purpose, but it is not suitable for the industrial application. This is the graph. The red color graph is that is shown here. That is for the on-off control. This graph, and this kind of train, this pattern is not suitable in the industrial application. Here for industrial application we want this kind of graph, orange color graph you can say. After response time is over, after it gets the set point value, it should work along the set point only. There should not be the error and vibrations or oscillations and all. This is the desired purpose for the industrial application, and this is achieved by the PID system, PID control system. PID is nothing but the proportional integral derivative. That this all we have seen. What happens when we use only P system, P control system, that also we have seen. There will be some steady state error, and when we use only P control system, and again some terminology we have seen. This is the rise time, this is the overshoot, this is the undershoot, this is the settling time, and this time shows the set point and all. This all we have seen. Now today, this also finally we have made a conclusion. When we increase the Kp value, the proportionality gain increases, oscillation increases, fast response will be there, but there will be steady state error. And for that, removing the steady state error, we are using the integral gain, and for removing the oscillations we are using the K loop to damp the oscillation. That all we have seen in the last lecture. Now today we are going to see the second part of the PID control, that is using the suitable simulation software. Here we have to do the simulation by using the software called as a Simulink. Simulink is one of the programming language within the MATLAB, which allows us to use the modeling, simulation and analyze of the system. We can analyze the system. Okay, again I will repeat this. Simulink, it is a programming language within this MATLAB which allows us to model, simulate and analyze the system. In the just like a MATLAB, we don't have to write a code here. There is no need to write the code, no need to remember the different syntax and all and coding. Just we have to choose some blocks, the desired blocks, and make a model and apply the simulation on that and analyze the system. Okay, there is a simple technique to have. Now directly, these are some points that we are going to cover today. Now directly we will go to the close this, close all these windows. Directly we will go to the MATLAB screen, and in the MATLAB screen there is simulation, Simulink library and command window. For going to the Simulink software, there are two ways to open the Simulink software. Either type here Simulink in command window and press enter, or directly you can choose here Simulink library. Okay, once you choose here Simulink library, here different functions are there in the Simulink library. See, here you can see this. This is the library browser, Simulink library browser, in which all the functions are arranged in an organized manner. Just like here common use blocks are there, here continuous, discontinuous. Under the if you navigate this, under the continuous category, these blocks will be there: derivative, integrated, transfer function and all. Under the discontinuous category, some different blocks will be there, and these are the source and sink. Source and sink, I will zoom it. The source and sink are more popular, that we require more. Now here source are there, and under the source, the functions are there which are used to originate the signal. Okay, under the source category, there are different functions that are used to originate the signal, just like step function. Okay, and under the sink, there are different functions that are used to end the signal, just like scope. Okay, scope we are using this. Okay, and if you want to, for creating a model, if you want to start with the blank model, just you have to go here, new model, click here new model. Okay, and the untitled screen will come, and you can do the you can choose the different blocks here and make a model and do the analysis. Now we will make some simple model, open loop model. Open loop model, we know that any mechanical system have at least three components: input, transfer function and output. Okay, now for input we will take, for input we will go to the source that I already told you, that are used to initiate the command signals. Hence we will go to the source, and in the source we will select the unit step function. Okay, now we will go to the transfer function, and for that we will go to the continuous. We will navigate the continuous, then we will see, then we will see here transfer function, and just drag it and keep it here. Now next, input, transfer function, then output. Output will be in the sink, and in sink that will be scope. We will choose the scope and keep it here. After this, now see here, for every block there are some, input signals, output signals are there. Just you have to the output connection. For transfer function there are input and output connection, and here you can see for some blocks there are multiple input connection, single output connection. For some blocks there are only single input, single output. That depends upon the blocks and application. Now here we want only single input and single output, if we will choose this. Now here you have to connect this, means just select here and join here. Just select, Okay, once the black color arrow comes, then connection is okay. Again you have to bring it here, click on here, and just now the connection is over. Okay, the connection is over now. Now after that, here we can change the names as well, or wait a minute, I will first zoom it. And here some different functions are there. This is for zooming, this is for fit to window, this is for sample time. Now I will use here fit to view. Okay, so that it is clear to you. And we can, if you double click here, you can edit this as well. Input, plant. Under the plant, it can be mechanical or electrical or rotational system, whatever, and this is the output. Okay, for the scope we will write as output. Okay, so you can shift this in horizontal or vertical direction as well. Okay, now here this shows simulation stop time. If you want to run the simulation for 20 seconds, you can say, or 10 seconds or 50 seconds, whatever, then you can change that from here. Initially we will keep it simple. We will keep it as 20. Then here there is a one, after simulation is there, or now press run to simulate here. Press run to simulate. Okay. Now here, once the here at the bottom of the screen ready word comes, means your simulation is over. And for getting the results, or here, but before going to the results, here it is showing one warning. You can check that warning. What is the warning says? The model until is using default value 0.4 maximum setup. You can disable the diagnostic by setting automatic solver parameter selection diagnostic to none. Means here it shows we have to choose a none option in the automatic solver parameter selection. Okay, you can disable the diagnostic by setting automatic control solver parameter selection to none. We will go to that. Here model configuration parameter, you have to go to the model configuration parameter, and then here diagnostic is there. What the warning is there? In the diagnostic you have to choose none. Okay, in the diagnostic you have to choose none. Automatic solver parameter selection, warning is coming there. Automatic solver parameter selection. Okay, that we have to choose as none. Okay, automatic solver parameter selection, that we have to choose as none. Apply and OK. Okay, then you can minimize this, and again you can run here. Here no warning will be there now, and now you can see the output. Just double click on the output and you will see. Now as we have choose here 20 seconds time, you can say, then the for 20 seconds its working will be like this. Okay, I will make it zoom. Now this on x-axis there is 0, 2, 4, 6, 8 up to 20, and from on y-axis there 5 to -5 value. Okay, and here as we have chosen unit step function, means after step of 1 it will rise. What is the meaning of unit step? It will take a step of 1. See here, this is 0, this is 2, and this is exactly at the center. Means after a step of 1 it will rise, and after that it will make a it will show the pattern. Now here there is it is no vibrations or oscillations are there, means it is okay. Okay, now I will close that, and we can change the here. Now here we have chosen only linear transfer function. You can change the transfer function as well to the second degree. Means suppose I want to have, suppose I want equation of the transfer function like this. You can change the different equation, just like suppose, wait a minute, suppose you want to have an equation like this. It's like layout. Suppose you want to have, you want to put a equation like this in the transfer function, then how can we do that? Just go to that transfer function, double click on this. Now here numerator coefficient, what is the heading? Numerator coefficient. What is the numerator in the PPT? S square plus 6x plus 10. This is the equation on the numerator. What are its coefficient? 1, 6, 10. 1, 6, 10 are its coefficient. Just you have to write 1, 6 and 10. Okay, this is for s square plus 6x plus 10, and here in below s cube plus 0 s square plus 7x plus 10, means here s cube coefficient is 1, then 0, then s coefficient of s, then constant. Okay, and just you have to choose here apply and okay, then it will show the equation like this. If its size is less, see, if you have chosen a block of means smaller size, then it will show only numerator and denominator, but if you drag it, it will show like this. Okay, now you can save it or directly run this. Okay, then we can see the output result. Okay, this way we are getting the output for 20 seconds. Vibrations are there. Okay, now this output screen or can be saved by here, and before saving you can change the style of the graph. Now suppose I will go to the style. I don't want yellow color, suppose I want blue color, because that looks good. And here number of axis will be 1 only, so don't take 2 axis, and just choose here apply and okay. See, we have chosen the blue color, it is showing blue color, and you can save this as well. Go to the print option, go to the print option, okay, here you can save it and print, and you just you keep right here okay. See what I will do, I will save it on the desktop only because I don't require it. I will give the name 001, okay, and save. I will say, and we will see on the desktop, where is that 001. Okay, this is the result. Okay, 0 to 1 it will be going horizontally. After that it will show the sudden jump, and slowly the pattern is going to increase, means oscillations, amplitude of oscillation is increasing. Okay, here you can if you choose this option auto scale, then it will show like this. And here means from here you can see that the amplitude is going to get increased, amplitude is increasing. Okay, continuous vibrations are having more oscillations. Now you can close this, and I will close this as well. Okay, now this was for open loop system. Now we have to learn the Simulink for PID control system, and we know that PID is for feedback control system. Hence we require, feedback is nothing but closed loop system, hence we require to have a closed loop system. Now for today we are going to have analysis for automatic voltage, analysis for automatic voltage regulator model of thermal power plant. Thermal power plant is there, and we have to regulate its voltage automatically. Now how can we do that? Okay, how can we do that? Just we have to make this model in the Simulink screen, Simulink window. This is the input, this is the output, and these are nothing but transfer functions are there. And for that, for this this transfer function is for amplifier. There are different devices are there in voltage regulator, just like amplifier, exciter, generator, sensors and all. Remember, sensor is always in the feedback path. Sensor will be always in the feedback path, and these are connected one to one. And here we have to connect, this is the new thing, that is the PID control. And here this is nothing but base voltage, means whatever the voltage is there, that if you want to have of more amplitude, then again in the output screen can be visible by adding the base voltage block here. Okay, now first of all we will make this model in the Simulink window, and after that we will do the analysis. Okay, wait a minute. Now, again we will go to the Simulink window, and I will, here you can press a control button, and or if you rotate the mouse ball, you can zoom in and zoom out. Okay, zoom in and zoom out. Okay, now what we have to do, I will make it smaller. I will zoom this. Okay, now what we will do, I will open that model diagram. This here, this is nothing but summing point, that we will add here summing point. For summing, addition of summing point, before summing point addition, we will add this transfer function, because that is easy. What are its coefficient? For first for amplifier, numerator is 10 and denominator is 0.1. Okay, that we will do. Now here just go to the simulation window, double click this, and here only 10 is there in the numerator, 10 is there in the numerator, and in the denominator I think 0.1 and 1, 0.1 and 1. Backspace, go to here denominator 0.1, space, apply. Okay, go to the 0.1, yes, S1. Okay, now again I want to have here it is 1 0.4. okay, again I want a new transfer function here. Now for getting for choosing a transfer function, either you can go by here by Simulink library, continuous transfer function, drag from here, or directly if you press this and choose the control button, you can make its copy. Again I will press it and choose the control button. I have made its copy. Okay, like this you can do. And now some rearrangement I will do. Okay, just I will keep it here. Okay, now next, what is that numerator here? I think 1 is there. 1 0.4, 1 0.4, apply. Okay, then 1 s plus 1 here. 1 s plus 1 means here 1 1 apply. For generator transfer function, and here for sensor 1 0.05. But before that I want to add here summing point. For summing point I want to go and the library commonly used blocks, summing points. This you can select here and keep it here. Okay, next here in the summing point, one thing you have to take care while choosing the summing point. Here it is plus minus. Now here it is plus minus, hence go to the that here simulation window, double click this, and this is 1 plus plus. Just you have to choose here, instead of plus plus, plus minus, apply, and okay, it will be 1 plus minus. Now I want to have make a feedback path. Okay, this is the feedback path. Okay, now and I want to add here another transfer function. I will choose this control and keep it here, and its coefficient are different, that I will choose from here 0.05 s plus 1, 0.05 s plus 1. Zero 0.05 delete s plus 1. Okay, apply. Okay, in this way we had made a model. Okay, one thing we haven't made yet, that base voltage and base voltage terminal voltage in kilovolt, terminal voltage per unit. Here it is showing terminal voltage in per unit, that we will write there, terminal voltage in per unit, terminal voltage per in per unit. I will copy this and put terminal voltage in kilovolt, terminal voltage in kilovolt, and we have to bring here again can be brought from the now we have to choose here gain point. This is basic testing. For that we have to go to the browser, and here common used blocks are there. Under the commonly used blocks category, you have to choose gain, and that gain simply I will drag it here. Okay, now join this. See, red color is shown when their connections are not okay. Till the connections are not over, now it's over, you can leave it. Okay. And you can change its value to 1,000. Apply. Okay. In this way we have made the model for the simile. Now we can have simulation. We have given time of 20. Now, PID we forgot to take. That is most important. Hence we will have arrangement for PID. We have to make space for PID. Just again go to the continuous PID controller. Just keep it here. Now it's okay. I will again go to that PPT and check whether all the things have at their position. Sending point is there, PID is there, and one. Okay, we haven't changed the name. We will change the name there. Amplifier amplifier. Second, exciter EXCITER. Third, generator. Backspace. Generator. Here, sensor. Save. Okay, we will save this. Where here I will make a folder name due to name as part 2, because this is part 2 video. I will give the name as part 2, and here untitled we will see. Untitled. Okay, under the part 2 we have saved it as untitled. Now just run this. Okay, no warning is there, and you can check here the output. Okay, output. Okay, sorry, we haven't given the values of PID. What I have told you, what is our target? Before using PID, the output performance of that controller will be like this. Okay, this red color. We will go to the main point now. Our performance of the controller will be like this, but for industrial application we don't require this. Okay, we have to choose. We have to convert this on and off path to this kind of path. Okay, that can be achieved by using PID control. And under the PID control, P means proportional, I means integral, and D means derivative. We have to change the values of Kp, Ki, Kd that we have already told you in the last video. If you want, you can go to that video. I will just quickly summarize that. Here, when you change the value of Kp and Ki, Kd you keep it 0, then the graph will be some kind of, you can see this graph. What is this? This is, I think, somewhat green color. And if you add Ki to that, then it will be like this. And if you add Kd to that, then the graph will be like this. Okay, means and these values you have to choose by trial and error method. Okay, trial and error method, and you have to see the performance. First of all, in the trial and error method, we are changing the value of Kp and keeping the Ki and Kd as 0. And once we get proper oscillations, we will change the value of Ki and keep it Kd as 0. That I will show you to one PPT, that you will understand better. Once you make a model, you have to go to the trial and error method. And in the trial and error method, first of all, we will keep Kp as 0, proportionality constant as non-zero, and remaining Ki and Kd as 0. And once we get the proper oscillations, you have to choose Ki is non-zero to reduce the steady state error. Okay, and to reduce the damping, to damp the vibration, you have to choose Kd as 0. Okay, you have to choose Kd as 0, because already we know the Kp value is responsible. This we have seen in the last video. The Kp value, proportionality gain, is responsible to increase the oscillations. And when you increase the Kp value, there will be the fast response and it reduces the sampling time. But at the same time, it will rise to overshoot. Overshoot will be more. Okay, this is the drawback of the Kp. Response will be fast, but the overshoot will be more, and at the same time steady state error will be there. To avoid that steady state error, we are using Ki integral gain to reduce the steady state error, and to reduce the vibration, to damp the oscillation, we are adding derivative gain. Okay, and these values, okay, can be chosen. Now see, this is the ideal graph 1, but see here, this is the graph you have obtained by changing only the Ki. This you have obtained green color by changing the, this is for Kp, this is for Kp and Ki, and this is for Kp, Ki, Kd. Okay, Kp, Ki, Kd. Okay, theory is over now. Now we will again go to that MATLAB screen and double click on the PID controller, and here we will keep it as 1. Initially we will keep I as 0 as well. Suppose this we filter coefficient as 50, sorry. Then you have to choose apply and OK. Apply and OK. Now run and again go to that. Now this is not the proper result we are getting. See, I have chosen here, there is one option called auto scale, option for auto scale. Okay, option for auto scale was there, and it is varying from 0 to 0.2, 0.4, 0.6, 0.81, like that. Okay, and the oscillations are slowly reducing. Okay, we have got the oscillations now, means I have to now save it. Now I have to save this. I will save this now. Okay, part 2. And how can we save that? That we have taken kp as one value, remaining ki and all rest 0, kp as 1, rest as 0. I will save it like this, and we will just check whether that has result of part 2. Okay, in the part 2 kp as 1. Okay, this kind of results we are getting. Okay, now here you can change the y-axis value as well. Just you have to go to the screen here, right click, and you will get axis properties, and here you can choose -5 to y minimum value as -5y. This I will reduce to -3 to +3. Okay, and apply. Okay, you can see here, or I will choose another instead of -3, that is -2 and 2. Apply and okay. What is happening? Okay, let it be. In this way you can change the values. Apply. Okay, now it's okay, correct. In this way you can whatever scale graph you want, you can choose. Okay, again I will choose this as well, because it is going from this we will do. This we will save. I will keep the same name and replace that original graph and close this. Now we don't want this kind of pattern. Already I have told you, I think one value is sufficient. From the looking at the result, we can say that one value is sufficient for kp. This we will keep as let us say 0.5. This I am taking randomly and checking. Apply and OK. I don't know the exact value that we want to take, and run. Once the ready mark come here, you have to go to the terminal voltage. Okay, 0 to 2. Okay, this pattern we are getting. Now I will save this. 2 to 3 pattern you have to save. For the submission point of view, 2 to 3 patterns you have to save. Here kp as 1 we have taken. Here we have taken ki as I think 0.5. I think I forgot what we have taken. Ki as I think 0.5. Half I will write. Ki as half we have taken. Whatever. Save. I will just check what the value we have taken and close this. Ah, 0.50. Then run. Then go to the terminal voltage and auto scale. Okay. Now again we will change the value. Now we have to damp the vibrations, means we have to introduce the KD. Suppose this is 0.5. I will change this value 0.7. Integral, suppose it is 1 2 I will take, and here I will take as 3. Let it be. Apply and OK. Then run. Then OK. Now in this way, different values of Kp, Ki, Kd you have to choose, and you can see the pattern. But this is not the desired pattern. This is not the desired pattern that we want to have. Okay, I will change the y-axis value. This property is -2 to -2 y-axis. This property -2. Apply. Okay. Here y-max is 3. I will take. Apply. Now it's okay. And I will save it. Okay. What the value we have taken? Okay. What was the value there we have taken? Okay, it is not showing. I have to first complete that task. Suppose Ki I think was Kp was 3 and this was Ki was 2 I think, and this is Kd as 0.5. So okay, K2 0.5. Okay, now again we will just check whether that result has been displaying or not. Okay, we don't want this kind of results, or I think more oscillations are there, means Kp value is more. The Kp value we have chosen, that is not okay. I think so. Means we will reduce the Kp value. 1 integral. Have you taken this value? 1 Ki as half, 0.5 we have taken. Okay, 0.3 I will take, and this 0.5 I will keep. Apply. Okay, 1 0.3 0.5, 1 0.3 0.5, run, and then see the result. Okay, now it's okay. Now see, suddenly there is a rise and some vibrations are there, and the vibrations are damped now. Okay, 0 to 1.5 we will change its pattern, and I will keep it as -1 and here 2. That is okay. Y-axis value 19. Now it looks good. Just we have to remove these oscillations, means some modifications we have to do. This is best graph I think we have got. In this way you can do the choose the different values for Kp, Ki, Kd, and okay, last I don't remember the name. I will just keep it as last and save, and we will again rename that. What was the values we have taken? 1 0.3 0.5 like this, 1 0.3 0.5, 1 0.3 0.5, Kp as 1, Kp as 1, Ki as 0.3 and Kd as 0.5. Okay, 0.5. Now I will stop this video here, and in the last video we will see we have taken different values of kp, ki, kd and different patterns we have got, and means trial and error method we have used here, trial and error method. And if you use the trial and error method, and after certain time you can get a proper curve, a proper means of response of the controller. But this is not a correct method. To remove this difficulty, there is one option called PID tuning that can be done in MATLAB software, that we will see in the next video. Okay, now we will stop here.